Good evening, everyone. Welcome to the concept portal, MCQ portal. And this is the second video on the MCQ series on graphs, circuit diagrams, and the diagrams, normal diagrams. And yesterday we started this. So saying that, okay, there's a lot of information which has been hidden in the circuit diagrams or maybe in the graphs or maybe in case of normal diagrams. And we need to unearth those hidden information, and we need to understand, okay, what clues do these diagrams give you, so that you can utilize it to correctly mark your MCQs. So yesterday we had done 17 questions from unit A, and in which the strategy which I adopted was something like reading the questions and then help you understand about what is the question about, and then also tell you what information you can extract from the graph, and finally, okay, giving the final answer. I'm not going to solve any question over here, okay, because we already solved several questions. You can go to my website, you visit my website and see from 2016 to 2024 November, all the questions have been solved, and maybe even this question would have been solved. If you want to find out what is the complete solution for it, okay, you can just go to that YouTube channel, okay, my YouTube channel, as you know, and then you can click on this, you can take up this particular question, part of the question, and put it in your search box. You will be able to get the solution for this. Okay, now let us start with this. So yesterday we did for unit 1, and today we are going to do with unit 2. Okay, so water at room temperature is placed in a freezer. Okay, specific heat capacity of water is twice the specific heat capacity of ice. So this is the normal way of how we solve a problem. Whenever I read some statement, I write the mathematical analog of it. Okay, specific heat of water, C water is equal to 2 times C ice. This is given to me. And assume the thermal energy is transferred from the water at a constant rate. What do you mean by it? Thermal energy is transferred at a constant rate. Whenever in the question there is a rate, which means what? In the denominator you will have a T over here. Okay, E by T. You would have studied rate of change of displacement, which means what? Rate of change. Rate means divide by T. Change of displacement will be S over here. S divided by T. It's velocity, right? In a similar way, whichever equation you take, if there is a rate, then definitely it will be divided by time. Which graph shows a variation with time of the temperature of the water? Oops, I did not start the timer. Let us start the timer also here. Okay. Right. Okay. So now there are 4 graphs given. You need to identify which is the right one. Of course, the answer is B over here. Now, first thing is that what is so special about this graph? What is the compare and contrasting feature of this graphs? You see here, there is a line here, there is a line here, okay, and there is a flat line here. What does this denote? Okay, see, this is at a higher temperature, then the temperature lowers down, it becomes a constant. What does it tell you? This could be in the liquid state, or maybe I can say this is in a water state, this is in a water to solid, that is water to ice state, this is complete in ice state. Okay, now if you look at these lines over here, what is the difference between each of these lines? If you ask me, see, if I just extend this one backward, now what do you see? These lines appear to be parallel, which means the slopes are same. Right? Slope are same. Now if you look at this one, now this slope is different, this slope is different, right? And if you look at this here, once again, this slope is same, these two are same. And here you see, this slope is different, this slope is different. Okay, 2 slopes which are same and 2 slopes which are completely different. Okay, that's what we have. Now towards it we need to understand. Now how do we proceed with this experiment, this particular question? So what we do is, let me maximize this a little bit more. Okay, now we know that whenever there is a specific heat equation, we'll always write this as E equal to MC delta T. Okay, and since I have E by T, I'll divide by T, I get this divide by T, and E by T is constant, which is already given over here. I can write power is equal to MC into what is delta T by delta T. Delta T is y-axis, delta small t is x-axis. This should be slope, right? So P is constant, M is constant. So only these two are the variables. So what will I write? I will write this as slope is equal to constant divided by C. So if C increases, slope decreases. If C decreases, slope increases. Now can C actually change? Of course, C will change. Why should it change? Because we already said water and ice. So basically you need to identify which of these diagrams is correct based on the slope. Okay, now I hope you would have got, you need to identify which slope is correct. Okay, now substitute the values of your see water and see ice, okay, and compare them, okay, which slope can be which one, and finally you can get an answer. I hope you got the answer by now. Okay, try it out yourself. So I'm not going to work out this solution. The next one, let us move on. A cell of negligible internal resistance and EMF 6 volt is connected to 3 resistors PQ and R. PQ and R is shown over here. R is an ohmic resistor. Don't immediately jump for finding out the resistance. Okay, so let us read the question fully. IV characteristics of P and Q are shown in the graph. IV characteristics shown. I is shown, V is shown. Okay, P and Q for both the elements. The current in P is 0.4 ampere. Okay, so this is a structured question. I just looked at the answer for what is the complete question of it. The complete question is something like show that, I'll write down, show that the current in Q is IQ is equal to 0.45 amperes. This is what is the answer. This is what is the thing that you need to show over here. Now how do we do this? Okay, now let us write down what is given here. Current in P is 0.4 ampere. So current in P is 0.4 ampere. You need to show that this current is equal to 0.45 ampere from the graph. Now towards it. Now first thing is that when this is 0.40. Okay. When there is a parallel circuit over here, what does it tell you? The potential at P is equal to potential at R. First thing. Okay. And secondly, you see this has been set 6 volt over here. Now you see this voltage here VQ plus this voltage should be equal to 6 volt, right? So I can now write VQ plus VP is equal to 6 volt. Now what has been given? The current here is going to be 0.4 ampere. Now what I will do is at 0.4 ampere, I will draw a line here. Okay, so this will intersect the point here, and I will get the voltage as 1.2, 1.4 over here. 1.4. So what is that we have done here? So we have already got 1.4 here. VP is equal to 1.4. So you look at the graph over here. So this is for the line P. I'm not going to extend this line over here. Okay. So only for this I'm going to do. And I've got 1.4 here. So I will now write this as 1.4 plus VQ is equal to 6. In fact, I'm solving the whole question because this question appeared to be a bit tricky. So I thought I will do this one. So VQ is equal to 6 minus 1.4, which should be equal to 4.6 volt. Okay, we have got the voltage at this point. Now from the graph once again at 4.6 volt, where is 4.6? 4.2, 4.4, 4.6 are somewhere over here. Drop a perpendicular here, it will intersect this line here, right? And find the corresponding current. When you find the corresponding current, you get this as 0.45 amperes, right? So therefore, this answer is 0.45. We have proved this. Okay, this is how you can solve this. Of course, the same question can be asked as an MCQ, wherein what they can do is they can give you all these values, and then the current in Q can be 0.6 ampere, 0.8 ampere, and so on. They can ask. Okay, most of the students commit a mistake over here saying that if this is 0.4, this also is 0.4, and finally they write this is 0.8, which is incorrect. The reason is because they get confused with what is a parallel circuit. A parallel circuit is one where the potential difference remains the same. Current may or may not remain the same. Okay, so take this into account. So we have used both the circuit diagram and as well as the graph to remove or extract the infographic. Now let us move on to the next one. So 4 identical resistors, each of resistance R are connected as shown. What is the effective resistance between P and Q? Between P and Q, you need to find effective resistance. What should you do? See, first thing is whenever circuit diagrams like this has been asked, what you do is between P and Q, just connect a battery. Though battery is not given, you can connect a battery here. When you connect a battery, what will happen? There's a current which has been extracted here. It's a current which is extracted over here. When it comes at this point, it branches into 2 parts. One part goes like this, one part goes like this, right? So why do I put this one here? The reason is because to understand which is a part of my series circuit, which is a part of my parallel circuit. So therefore, as you see here, so this same current comes over here, the same current comes here, the same current comes here. Let us say if this current is 1 ampere over here, this is also 1 ampere here, also 1 ampere. I am just giving an example, okay? You need not substitute the same value. But here the current is different. So therefore, this whole thing is seen to be a series circuit. If this is a series circuit, what I can do? I can now find out that I can put this resistor as such R here, and I can find out what is the effective resistance here. What is the effective resistance here? This would be 3R over here. And then this two appears to be parallel. And now I can find out between these two what is the effective parallel resistance, right? So the answer is going to be 3r/4. You try it out the solution. Next question. The diagram shows for a region of a Earth's surface the incident radiated and reflected distances of solar radiation. So 600 is given here, 450 gets radiated, reflected is 150 over here. What is the albedo of the region? Okay, what is the albedo? Albedo tells you the ratio of I scattered divided by I incident. So what is scattered? Scattered means, what's the difference between a scattered and reflected one? Scattered means, okay, so it can get scattered, can get reflected in many directions, while reflected means, okay, a parallel beam of light falls onto a mirror and once again goes like this. Okay, so therefore, so this value would be 150 divided by 600, which is 1/4. Solve this question next. Okay. 4 identical lamps are connected to a circuit. The current through the lamp is I. The current through the lamp is I. Do not take this current. Okay, the current through the lamp is I. So this is your current I. Through the lamp L is I. I'm sorry. This is your Li over here. And here it says 4 identical lamps. See, when you say 4 identical lamps, so all this are 4 identical. So therefore, similar to this, you also have this. So this current should also be I. Which means immediately you can say that this current should be 2I. Right? Okay. Next. The lamps are arranged using the same cell. Okay. Now what they are doing is that they are arranged using the same cell. What is the current through L over here? What is the difference over here? See, the difference is you had a parallel circuit initially like this and you had a battery to the external circuit. Now what's happening? Now you see these two circuits, okay, so they are being pulled away like this and this is being pushed inside over here. If you want, I can write down the transition diagram as how this circuit and this circuit are both one and the same. Okay, if they are one and the same, the current through the L is same only. Okay, that's what it says. It is nothing but I. Now, how do you arrive at it is a question over here. Okay, so because when we initially look at it, okay, we don't get it, but let us understand what we do. What I do is I take this connection, I'll put it over here. I put it over here, right? So this connection, I put it over here. Okay, so I can shorten the wire and put it over here, right? So therefore, I've got something like this. Next, what I'm going to do is I am going to rotate this one by this way, by 90 degree, which means what? I have one here, then one here, and then one here, and the other one here. And then in between, you have a battery here. Next, what I can do is very similar to it. Now pull this one this side and pull this one this side, right? Which means I'll pull this one here and pull this one here, pull this one here, right? I'll pull this one here and pull this one here. And this battery would be like this. And then similarly, I am going to do the same thing. Pull this one here and this one also. This one also. I am going to pull it like this. Pull it like this. Don't you see that these two are identical? So the current through it is I. Okay, there's not much of calculation. The same thing you have to repeat it. Now, okay, the black body radiation curve of an object at 600 Kelvin is shown. The intensity units are arbitrary. Okay, black body radiation is shown over here. What is the radiation curve of the same object at 450 Kelvin? This is done for 600 Kelvin. Okay, why is the graph given to you? Because what is this wavelength over here? So we know whenever there is a black body radiation given, lambda into temperature is equal to constant T, right? In other words, lambda should be equal to B by T. So what does it tell you once again? It tells you when T reduces, lambda increases, right? Now we need to look at this over here. Okay, most of them think that B is correct. The reason is because they always look at something like, okay, that the intensity rises, because you don't get any information about the intensity. Do not worry about that. Okay, so therefore, now what you have is, you have the lambda should increase. Okay, as compared to original one, the lambda should increase. Now look at the peaks over here. Say this peak, for example, this is the lambda. This is the original lambda. Okay, let me call this a lambda O. The new lambda is somewhere over here. This lambda is larger than this. This is the new lambda, right? So lambda n is greater than lambda naught. So A is the right answer. You can check this if you want the rest of them to confirm that, okay, but whether these are all the same or do we follow a different rule, right? Next, the resistance of a component X decreases when the intensity of light is incident onto it. Okay, so there is a LDR over here, light dependent diode. Okay, resistance, and when the intensity of light is incident on it, you see that the resistance Rx decreases when intensity, this is not current, it is intensity, increases. X is connected in series with a cell of a negligible internal resistance and a resistance of fixed resistance. Okay, I put a fixed resistance over here. This is one more element, voltmeter and ideal. This one ammeter are ideal. Okay. What is the change in the reading of the ammeter, the reading in the voltmeter when the light incident on it is X is increased? So what's happening over here? When the intensity of light is increasing, Rx will reduce. So X will reduce. When Rx reduces, what happens over here? The resistance reduces, resistance of the total circuit reduces. When the resistance of total circuit reduces, what happens? The current will increase, right? The current will increase. When current is increasing, then what happened to this? This drop across this I times R also increase. Okay. Now, but this is constant over here. Let us say, for example, if this is given as 10 volt. Okay. Now, initially, let us say when no light was falling onto it, let us say here it was seen to be 4 volt over here. Okay, when no light, with no light, let me say this VR was seen to be 4 volt. When light is incident onto it, what happens? More amount of current is passing through it. So how much can you expect here? Current is increasing. Is the resistance increasing here? No, resistance not increasing for this one. So this should become 6 volt over here. If this becomes 6 volt, what is the voltmeter record? See, this should be, so here, this should be 10 minus 6, which should be equal to 4 volt. Earlier, what was it recording? It was recording 10 minus 4, which is 6 volt, which means what? The voltmeter is now seeing a reduction in the voltage, right? So what should we see? See, current increases, voltage decreases. Where did I get this idea from? I should understand how does the circuit perform, right? Okay, let us move on to the next one. 3 lamps X, Y, Z are connected in the circuit. The EMF of the cell is 20 volt. 20 volt. Internal resistance of the cell is negligible. The power dissipated by X, Y, and Z is 10, 20, and 20. So this is 10 watt. This is 20, and this is 20. Okay. Now 3 lamps are given. Okay. Now what is being asked? What is the voltage across lamp X and lamp Y? The answer should be B. Okay. Lamp X and lamp Y. What is it now? Now, when you say the power across this is 20 volt over here, 20 watt over here, and 20 watt over here. These are parallel resistances, right? Parallel ones over here. Nothing has been told anything apart from it. Now you see, the voltage across these 2 points should remain the constant, which means what? Your Vy should be equal to Vz. Okay. And what is to be found is this one. Okay. Vy is equal to Vz. Now if I multiply by the current I times Vy is equal to I times Vz, which should be equal to V. So they got this. That means the current through this is identical in both the branches because the wattage should be the same. The current should be the same. So if this is current I, then this current should be 2I, right? The rest is history, which you already know. So you can just write for this one as Px is equal to 2I into R, right? And then for this one, or maybe you can write, you can write like this, and then 2I into Vx, not R. Okay, 2I into Vx, current multiplied by voltage. And for this, what you can write is you can write Py is equal to Iy into Vy. Now you can divide one by the other, right? So this Iy is I, you can divide one by the other, and you can get Vx by Vy. And what has been asked? Vx and Vy has been asked. Then you can find out the next step. I'm not going to reveal you. You can use this Vx plus Vy is equal to 20 and get the values of Vx and Vy. Okay. The correct answer is seen to be 4 volt and 60 next. A cell of negligible internal resistance connected to 3 identical resistors. Okay. The current in the cell is 3 ampere. Current in the cell is 3 ampere. 3 ampere. Resistors are now arranged in series. What is the new current in cell? Now, so if you are connected in parallel, this is the current. If you are connected in series, then what is the new current? That's the question. Now the question that we need to ask is, see, something changes over here. What is changing? Resistance is changing. Now the question that you need to ask is, what does not change? Right? What does not change? You are not changing the battery over here. Which means what? The voltage is constant. That is what you need to use here. Right? So therefore the clue here is voltage does not change. So if this is resistance R, this resistance R, this resistance R, initially you see R and R parallel become 1.5 R, and then this is an R here. The total resistance will be equal to 0.5 R plus R, which should be equal to 1.5 R. 1.5 R, and if this is the current passing through it, multiplied by 3 amperes should now be equal to V, right? Now, if suppose all the 3 are connected in series, one here like this, one here like this, one here like this, and then the same battery is being used, then what will happen? You can say effective resistance will be 3R. 3R multiplied by what is the current here? I do not know. I need to find. So this I should now be equal to V. Now equate these two. So 1.5 R into 3 R, 3 amperes should now be equal to 3 R multiplied by I, and cancel the R, get the value of I. Right? So by this you can easily find out what is the answer. The answer is 1.5 ampere. Let us move on to the next one. The design of the pad encloses the resistor in a material that traps here. This is once again a structured question, but I found out to be good enough, so I included here. The design also places the resistor close to the surface of the pad. Okay, this is the resistor shown. There is a diagram shown over here, and then explain with reference to thermal energy transfer why the pad is designed in this way. Now he gives you an actual way of a pad. Now what is being shown? The resistor is not midway. It is nearby to this mat over here. There's a lot of gap in between. Okay, there's a resistor and there's an insulator, and it says a material that traps air. Right. So whenever you have a material that traps air, and he is asking about a question on the thermal energy. What does this tell you? This tells you that air is an insulator. Okay, that's the first thing. So explain with reference to thermal energy why the pad is designed in this way. Okay, you can just say air is an insulator, so therefore it does not conduct. First question. And secondly, okay, and then you need to trap the air over here. You need to trap the air over here. Design is also, what's the next one? See, where the cat sits, this distance is much smaller. This distance is much larger over here. Okay, this is thinner, this is thicker over here. So why is this being kept? The reason is because when you have air for a longer distance over here, okay, then what can happen is the convection will not happen. So in order to prevent the convection, they kept like this. Okay, and then secondly, now what does it says? The design of the pad encloses a resistor in a material that traps air. So materials, there are two types of material. Okay, one is an insulator, the other one is your conductor. Okay, you can say there's a mat which has been kept over here, which is an insulator. So why do you keep an insulator? A thermal insulator keeps the heat as such. So therefore, the heat is not being lost. So that is what is required. So hence an insulator has been used. So this is for 3-mark question. So you can easily put all the 3 information over here. Okay, showing you about the ways of thinking how to answer some question like this. Next, 2 power supplies, one of constant 24 volt of EMF 24 volt, other of variable EMF P, other of EMF P, are connected to resistors. Okay, both power supplies have negligible internal resistance. Okay, 0 internal resistance. What is the magnitude of P for the reading of the ammeter to be 0? Okay, what could be the value of P? Now when you have some questions like this, okay, so what happens over here? The current comes like this, it comes here, and it should actually branch here. He says ammeter should read 0. So it does not branch, all the current goes like this over here. When will this happen? This will happen if the potential difference at this point and potential at difference at this point, potential at this point and potential at this point are equal, right? Which means the potential at this point and this point, or maybe if you take the potential difference here and the potential difference here, then if they are equal, definitely all the current will pass like this only. Which means what? If you want to find this one, I can now write Vp is equal to, let me give some nomenclature here. I'll put APC over here. Now this Vp will be equal to Vpc. Okay, so if you get this value of Vpc, you can equate it to Vp. How do you get this value? Which is nothing but you can use the total current. You can find out the total current as equal to the total voltage divided by total resistance over here, which would be 9 plus 3, which is 12. And then what you do is you find out the voltage across this, which would be equal to I times 3. Okay, so by making use of this, you can get the answer. The answer is 6 volt. Next, in the circuit shown, the cells have the same EMF and 0 internal resistance. All resistors are identical. Okay, what is the order of the increasing power dissipation in each circuit? Okay, so you need to find out the power dissipation. Now, each of them have the same resistance. Now you see, they have the same voltage also, right? They have the same voltage over here. So therefore, if they have the same voltage, now I want to find the power dissipation here. This is V here. What is the power dissipation across this? This should be V square by R. There is one more also here. So V square by R. So what is the total power resistance? 2V square by R. Total power dissipation. Here what should be the power dissipation? So he is asking for the total power dissipation. So don't worry about whether there are 2 resistors, 3 resistors over here. Just calculate the resistance in series and get the answer. So this should be, once again, this is V. So it will be V square divided by 2R. The next one, If you look at this here, circuit Z here, there are two resistance here, which is R and R. So which would be effective would be 0.5 R, and this would be R. So this is the power dissipated from here to here. Full circuit is asking will be V square divided by 1.5 R. What's the next step? Okay, next step you can decide it, right? So you can put the values and you can find out what is the answer, right? So the answer is YZ. Next. A thermodynamic cycle consists of an adiabatic, isothermatic and isothermal process. This is a HL question. Okay, is shown. Which of the following correctly identifies the processes of the cell? The answer is C. So how do you do it? Now what all this in your adiabatic? Remember, in a PV diagram, adiabatic compression or adiabatic expansion will have a more steeper curve like this. The most steeper curve will be adiabatic. So therefore, you see, this is not steeper, this is not steeper. This is the most steepest one. So definitely this is your adiabatic. Adiabatic. Okay. Then isovolumetric. What do you mean by isovolumetric? That means the volume is a constant over here. Okay. So then isothermal process. What do you mean by isothermal? So first, okay, let us look at isovolumetric. Look at this vertical line here. See, the point, at this point, the volume is some value. At every point over here, it's the same volume, right? Pressure is changing over here. So definitely this should be your isovolumetric. And this is the, now I already said isovolumetric, adiabatic, the last one is isothermal. So this should be isothermal. Okay, whether you know it or not, you can just mark this isothermal. Now what we'll do is let us look at this here. Okay, you can look at this. Okay, Z2X, first one I'm confirming Z2X is adiabatic. The rest of them you can look into it and consider the answer. Now let us move on to the next one. The diagram shows two cylindrical wires. Wire X has a length L, diameter D, resistivity rho. Wire Y has a diameter 2L, D by 2 and rho by 2. So what is the resistance of X versus Y? Simple question. What you need to do? Find R using this. How do you do? Rho L divided by A. What is A here? See, remember, this is diameter D. This is not area. Okay, so how do you find area? Area is nothing but pi D square divided by 4, right? Because D is the diameter. So you are using pi R square, which I am writing as pi D square. In a similar way, substitute this value, divide one by the other and get the answer. The answer should be 0.25. Okay, let us move on to the next one. These are called as comparison problems. Usually in most of the papers, you can find one or two problems which are comparison problems. Now, next one. In a climate model for a planet, the incoming intensity is 400. This is 400. Intensity radiated is 300. Radiated is 300. Then what is the value of the reflected? The temperature of the planet is constant. What are the reflected intensity from the planet and the albedo of the planet? Okay, this is the question. So therefore, now what is the reflected? See, for example, 400 comes in, 300 goes out. What is the reflected one? 100. Simple. And what is albedo? Albedo is nothing but 100 divided by 400, which is 0.25. Already saw this, right? So therefore, the answer is B. The answer is E. So 100 divided by 400 should be your alpha. Okay. For this, you should know what is the definition of alpha. A cell of negligible internal resistance and EMF 6 volt is connected to three resistors RP and Q. RP and Q. R is ohmic. Okay, this we have already done. Okay, we are not going to do this. Right. Next. Two cells are connected in parallel, right? As shown, each cell has an EMF 5 volt, internal resistance of 2 ohms, 2, and then the external lamp has a resistance of 4 ohms. Ammeter is ideal. What is the reading of the ammeter? Okay, see, there is a general formula for solving such problems, which I will tell you. First, when you have two cells which are parallel together, circle this. Okay, first to simplify this one. So, how do you simplify this? So, this would be simplified as equivalent to one cell, one resistance. This you got as E total, this you got as R total, and then you take the external circuit. Take the external circuit, the ampere, and then put a lamp here, like this over here. This should be the total one, and from here you can find out what is the current. The formula for this is given by E total divided by R total is equal to E1 by R1 plus E2 by R2, where R1 and R2 are the internal resistances. So what I am going to do is E1, I will solve this 5 by 2 plus 5 by 2. Okay, because positives are being joined, positives are being on the same direction. So this will be 5 by 2 plus 5 by 2 would be 10 by 2, 10 by 2, which should be equal to 5. Thus E total will now be equal to 5 times R total. What is R total? 2 ohms and 2 ohms parallel to each other. What will this be? This will be 1 ohm, right? So this should be 5 multiplied by 1, which is equal to 5 ohm. Now we have got E total, which is 5 ohms over here, 5 ohms over here. I'll write it properly, 5 ohms, and R total, which is 1 ohm over here. And then what is the bulb resistance? 4 ohms over here. So what's the current? Current I is equal to 5 volt divided by 4 plus 1, which is 5. The answer should be 1 ampere. Then 4 resistors of 4 ohm each are connected as shown. Okay. What is the effective resistance between P and Q? Effective resistance between P and Q. So what should I do? Between P and Q, I told you in the previous problem also, I am going to put a battery here. Put a battery here like this. Okay. So no need to put it over here. You can just put it here itself. So if this is positive, the current will come here. This current comes here. It branches over here. So it's quite easier in this case. So find out what is the effective resistance here, right? Effective resistance would be R by 2 here. Now this will be R plus R by 2. Now your circuit will look like this over here. This will be your P, this will be your Q, and this will be R plus R by 2 would be 3R by 2. One more resistor. Now you have this is R and 3R by 2. You just take a what you call you just take the parallel resistances and get the formula. Substitute the value of R over here, 4 ohms, and you get the answer. Okay, maybe here itself we can substitute. You can say this would be 4 ohm, this would be 6 ohm over here. 4 into 6 divided by 4 plus 6. Do it, you get the answers 2 points. Let us move on to the next one. And planet has an albedo of 0.3. A simplified energy balance for the planet is shown. Okay, what is the intensity radiated by the surface of the planet? Surface of the planet, what is the intensity radiated? Now you see 100 comes over here, then 60 goes upwards. Sorry, then so part of it gets reflected. Okay, and 60 once again comes over here. So as a result of this, now what is being given over here? It says 0.3. 0.3 is the albedo, which means what? I scattered divided by I incident is equal to 0.3. So I scattered or reflected should be equal to 0.3 multiplied by 100, which should be equal to 30, right? So it means 30 units is getting reflected. But so therefore, what is being retained? Retained is 70 over here. Okay. Now once again, you see the part of it is now getting reflected from the atmosphere. Out of when 100 comes over here, okay, so it gets reflected over here. So 60 comes from the reflection. So this 70 plus 60, which will be equal to 130. 130 is a total absorption seen in the planet, and all this 130 gets reflected over here, right? Considering this is a black body. Then D. Conductor X is connected to a cell of EMF E. A power of 16 watt is dissipated in X. Okay, so this gives you Px is equal to 16 watt. Conductor Y is made from the same material with the same diameter as X, but is twice as long. Okay, so when you say twice as long, what has been asked over here? So somewhere it tells you about the resistance. Resistance is proportional to L. Area is not changing. So therefore, first one has a resistance R, second one has a resistance 2R. Then both cells have negligible resistance. What is the power dissipated by? Quite easier. So you can easily find out. So Px equal to 16 watt, which is nothing but E square by R, right? And what will this be? Py will now be equal to 2E the whole square divided by R. What is 2R? 2R over here. Substitute the values and get the final answer, right? So you will get 4E square by R. E square by R equal to 16. 2E square by R would be equal to 32. So answer is C. Next. Two resistors of equal resistance R are connected with two cells of EMF E and 2E. Both cells have negligible internal resistance. Okay. What is the current in the resistor labeled X? This question. So what you do is, this is 2E here. You need to find out what is the current here. Now the same potential difference is also being seen here, right? For same potential difference, which is what I will do is I will write like this. I will write like this over here. I'll remove this resistor and put the battery here. I will put the battery here. Now this is E. This is 2E. If you want to keep the resistance, what you can do is you can keep it at the back also. You can keep it at the back, right? I can shuffle the resistance and battery like this over here. Now if this is 2E and this is E, what will happen? This will send a current like this. This will send a current like this, right? So this will send a current of 2I over here. And this will send a current of I over here. I will not consider this one. This will be confusing for you. I'll remove this because I am just considering the potential difference. This will send a current of 2I over here, 2I here, and I here. the result here would be subtraction of these two would just be equal to E by R, right? So answer is E by R. Next. A solid is heated at constant power in an insulated container. The graph shows a variation in temperature and time. Okay, why is the temperature constant for this section Q1? Now, whenever you say temperature is constant, what is that you should understand? When temperature is equal to constant, temperature is a measure of kinetic energy. Kinetic energy should also be constant. Do we have anything like this? Intermolecular potential energy of the molecule is constant. No. Why? Because when there is a phase transition taking place, what's happening over there? The molecules are now changing its positions, right? Either they are coming nearby or they're moving farther away. So in this case, it's moving farther away because temperature is rising, right? So therefore, this is incorrect. So B should be the right answer. Okay, think about it and answer it appropriately. Then, two flasks P and Q contain an ideal gas and are connected with a tube of negligible volume compared to that of the flask. The volume of P is twice of the volume of Q. Vp is equal to 2 times Vq. Okay. P is at a heated temperature of 200 Kelvin and Q at a temperature of 400 Kelvin. So what is now given? Tp. So this is kept at 200 and this is kept at 400. Now before that, look at this connected tube of ideal gas. What do you mean by ideal gas? Any question which has an ideal gas, which means that you can always use PV is equal to nRT. This equation can be used, right? So therefore, what is the mass of gas in P and mass of gas in Q? We always know that the number of moles is directly proportional to mass. Number of moles is directly proportional to mass. So now what we can do is PV is equal to nRT. You have P. Is the value of P changing? No, P is not changing. So P is not changing. What's the value of V? V is nothing but Vp. Vp, I'll just keep V here. Should now be equal to mass in P. Let me write this as Np. Okay. And then R. R is not changing. T. What is T? 200. 200. And so second one. Second one, what do I have? P is same. Then this one would be half of Vp. Right? V by 2 is equal to. Now once again here, it will be NQ. NQ into R into 400. Now cancel this, simplify it, get the answer. The answer should be move on to the next one. Okay. A variable resistor is connected to a cell with an EMF E, right? And internal resistance R is shown when the current in the circuit is I, the PD measured across the terminals of the cell is V. Okay, so when the current in the circuit is I, PD is V over here. The resistance of the variable resistance is doubled. So you are aiming to increase this from R to 2R. What is true about the current and PD? Now what you are going to do? When R is doubled, what will happen to the current? Current will definitely reduce. I will reduce. Now, what happens here when current reduces over here? Is the E value changing? E is not changing. Is the R value changing? R is also not changing. What do you call this one as? This is nothing but your TPD. What is TPD? Terminal potential difference. Potential difference means it is the potential difference that you measure across the terminals of the battery. Okay. So therefore, now what's happening to this value? This value V is given by E minus IR. When I reduces, definitely this IR will reduce. When this reduces, V will increase. Right? Potential difference. The voltmeter will read a larger value. Right? Okay. The voltmeter will read a larger value. So greater than V. These two should be correct. These two should be incorrect. Next one. So between these two you need to select. This is where the actual question comes into. Greater than I by 2, less than I by 2. Now what happens over here? So when you say I is lower, now let us write an expression for I here. So what do you do here? I is equal to E divided by R plus R. This was the original expression, right? The total EMF divided by total resistances. Now when this R is increased to twice, your I dash will now become E divided by 2R plus R. What will this I dash become? I dash, will it be less than I? So let us say for example, here the resistance is much larger. So I dash will now be, so if I make this is 0, so this should now be E by 2R, which should be equal to I by 2. Okay. So as a result of this, what will happen to this I dash? I dash will definitely be larger than this. So therefore, A is the right answer. Larger than I by 2. Next one. The EM spectrum radiated by a black body at temperature T shows a peak at wavelength lambda P. What is the variation of lambda P versus T? So what is being shown? So when you say black body, lambda into T is equal to your constant, which is known to you. Now he is asking you which graph will show you. Okay, when you say lambda into t equal to constant, which means this is lambda is y axis and this is x axis is equal to constant, or y is equal to constant divided by x, inversely proportional. A is the right answer, right? So this is directly proportional. This is also directly proportional. Y equal to minus mx plus c. This is a chaotic curve which you cannot have it.